Welcome to this explainer. Today we're tackling a genuinely fascinating problem. Think about it. How on earth do we translate the completely chaotic, invisible motion of gas molecules into perfect, logical, mathematical sense? I mean, it sounds kind of impossible, right? Gas particles are literally constantly zipping around, colliding, bouncing off each other in total macroscopic pandemonium. But, as we're going to see by breaking down these source materials, there's actually a hidden, beautiful order to all this chaos. We are going to decode exactly how molecular speeds are distributed. And we're going to build this concept step by step. Our agenda for today: first, we'll look at the chaos of collisions. Then, the anatomy of the speed curve. After that, finding the peak velocity, turning up the heat, and finally, why lighter gases move faster. Let's get right into it.
All right, Section 1, the chaos of collisions. Let's dive in and understand what actually drives molecular movement.
So, quick question for you. How fast is the air around you moving right now? Take a second and just look at the air in your room. It probably seems completely still, right? Perfectly quiet. But I want you to contrast that macroscopic stillness with the microscopic reality. Down at the molecular level, it is absolute, unyielding chaos. Particles are darting in every possible direction, constantly crashing into one another. But what exactly is fueling all of this frantic activity?
Well, the source material lays this out as a perfectly logical chain reaction, and it all starts with temperature. You see, temperature acts as the fuel. It provides kinetic energy to the system, and that energy, it directly drives the motion of the molecules. Now, because you have literally billions of particles moving around in a confined space, that motion inevitably results in endless, constant collisions. It's just bang, bang, bang. So, temperature to energy, energy to motion, and motion to collision. That right there is the fundamental engine of a gas.
And because of this constant engine, the source notes reveal a really surprising hard and fast rule about this environment. Exactly 0 molecules have 0 velocity. None. At any particular temperature, these particles are in a constant hyperactive state of motion. The environment is so incredibly dense with collisions that the split second a particle might theoretically stop, boom, it's immediately rear-ended by another particle and sent flying all over again. Complete stillness? It simply does not exist here.
Moving on to Section 2, Anatomy of the Speed Curve. Let's see how this all builds into a graphical representation.
Okay, so to actually make sense of billions of random collisions, we use a specific graph called the Maxwell-Boltzmann distribution curve. Now, before we look at the shape of the curve itself, let's break down exactly what we're measuring. Along the x-axis, we're plotting velocity. That's the speed of the molecules, moving from 0 to increasingly faster speeds. And on the y-axis, we are plotting the fraction of molecules that are actually traveling at that specific speed.
When you plot this out, a very specific bell-like shape emerges. Think of it kind of like a massive microscopic highway. According to the notes, a very small fraction of molecules are moving way too slowly. You know, the grandmas in the slow lane. And another very small fraction are moving way too fast, the reckless speeders. But as you move up from those slow speeds, the fraction of molecules initially increases with velocity. It hits this massive peak right in the middle, and then it sharply falls off. The vast majority of particles just clump together right there in the middle, cruising at a very similar, average highway speed. Now, what's genuinely fascinating here is the geometry of the curve itself. If you look at the total area under this curve, it actually represents something physical. The total area always equals exactly 1 if we're talking about a fraction, so representing 100% of the gas. Or it equals n, representing the total number of particles in the entire system. Basically, this curve encompasses every single molecule, from the absolute slowest crawler to the absolute fastest speeder, all bound together in this single mathematical shape.
All right, Section 3, Finding the Peak Velocity. Let's figure out how to pinpoint exactly where our largest group of molecules actually is.
We call this peak the most probable velocity, or UMP for short. Put simply, this is the specific speed possessed by the maximum number of molecules in a gas at any particular temperature. Think of it like this. If you were to reach into our invisible gas blindfolded and pull out just one single molecule, this is the speed it's most likely to be traveling. It's the very tip, the absolute highest point of our entire speed curve.
So how do we actually find it? Well, the source outlines a beautiful little bit of calculus to solve this. First, you take the mathematical function that creates the curve itself. Then, you differentiate that formula. And here is the magic step. To find the peak of any curve, you just find the exact point where it stops going up and hasn't yet started coming down. It's the exact point where the slope equals exactly 0.
By setting the slope to 0 and solving for u, the velocity, we mathematically nail down the absolute peak of all that chaos. Which brings us to section 4, turning up the heat. Let's make things a bit more dynamic and explore what happens to our math when things get hot. I want you to imagine injecting more thermal energy into our system. At our initial lower temperature, T1, the curve has a slower peak speed, it's very tall, and it has a narrow width. But what happens when we increase the temperature to T2? The kinetic energy absolutely surges. The peak speed gets faster, shifting the whole thing to the right. But notice what else happens here. The height of the peak becomes much shorter, and the entire curve broadens out significantly. The molecules are essentially spreading out over a much wider range of high speeds.
So the absolutely crucial point here is summarized perfectly by a quote from the source material. Remember how the area under the curve is always the total number of particles? Well, because the total number of molecules remains exactly the same at both temperatures, they have to go somewhere when they speed up. The fraction of molecules having lower speeds decreases, and they redistribute. So the fraction of molecules in the higher speed ranges increases. The whole population just upgrades to a faster bracket, which forces the curve to flatten out and stretch. And finally, section 5. Lighter gases move faster. What if we keep the temperature perfectly stable but change the gas itself?
The notes give us a direct comparison between two entirely different gases at the exact same temperature. A heavier gas is going to have a lower most probable velocity. Its curve is bunched up, shifted to the left, basically acting a bit sluggish. But a lighter gas, it has a much higher most probable velocity, shifting its entire curve to the right, and this brilliantly illustrates a core law of this macroscopic highway. At the exact same temperature, with the exact same amount of thermal energy fueling them, a lighter gas will always move faster than a heavier one. It just takes way less energy to get a lighter particle zipping around.
So we've managed to translate invisible, completely chaotic collisions into a beautifully structured curve. We've found its peak, and we've watched it shift with heat and mass. But I want to leave you with a thought as we wrap up this explainer. You never actually see these molecules, but this chaotic, microscopic speed distribution, this exact mathematical curve, governs literally everything. It dictates the transfer of heat in your home, the pressure of the tires on your car, and even the unbelievably complex weather systems in our atmosphere. So next time you look at the still air around you, ask yourself, how is this invisible mathematical distribution completely dictating the physical world you experience every single day? Thanks so much for exploring this with me today. Keep wondering and keep learning.